For concept 4, we're going to take a look at some special cases. We're still factoring, but these are special situations. So up at the top here, I want you to write special cases. Yoink, yoink. These are special situations that you will see sometimes that require just a special knowledge of what's happening in the problem and knowing that it's a little bit different than the other methods that we've learned. The other methods that we've learned so far are really consistent and they work pretty much no matter what, as long as you have 3 terms. But what if you don't have 3 terms? Or what if the 3 terms that you have are super special so you don't have to go through that big huge X process? That's what we're going to look at today. Starting with this video, part 1, we're going to take a look at what we call difference of squares. So let's dive right in. When you are dealing with a difference of squares, you have to ask yourself a certain number of questions, okay, just to see if this is the case with the problem that you're working on. So to find out, is this a difference of squares, the first thing you want to ask yourself is, do I have 2 terms? And that would be instead of 3. We've been dealing with 3-term polynomials so far. Now we're going to jump into, okay, well, what happens if we only have 2 terms, like this? Do I have 2 terms? Are those terms, so each terms, are they, let's see, are they being subtracted? This is why it's called a difference of squares. Are they being subtracted? Then, if they're being subtracted, you have 2 terms, they're being subtracted, then you're going to look to see, is everything in the problem a perfect square? What am I talking about when I say perfect squares? Well, remember, and I'm going to write these off to the side here, you need to have these memorized. So, what are we talking about? 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, and 12 squared, last but not least, is 144. So, all of your squares, perfect squares from 1 to 12, you need to have them memorized. It's extremely important because once we move forward, you're not going to have time to sit and count on your fingers and figure out is there something I can multiply by? No, you just need to know them, be able to recognize them and see them quickly. All right, so memorize these. We may or may not be having a quiz on them. Timed quiz. I don't know. You just never know what I might pull out of my hat. So make sure you get those memorized as quickly as you can. So you're looking to see, is everything in this binomial a perfect square? Then once you've established that yes it is, or what if it's not? If it's not a perfect square, then you ask yourself, can I take out a GCF? If I take out a GCF, then do I have perfect squares? That's what you want to see, because we are looking for a difference of squares. If you do, then you're going to factor it in this special way where the factors will be the sum, meaning addition, and difference of the 2 roots. Okay? So we're going to take a look at some of these problems together. We're actually going to work, this video will go through number 78, and we'll take a look at what I mean by this. So let's dive right in with number 71. 71. All right, couple of questions. Number 1, do I have 2 terms? Well, let's see. I have 1 here, and I have 1 here. Are those 2 terms being subtracted? Is there a subtraction sign in the middle? Yes, there is. Notice that this time, because I know I'm looking for subtraction, I'm not attaching this negative to the number. Usually, normally, we would say that the sign stays attached to the number, but in this case, since I know I'm looking for subtraction, I'm going to leave that sign alone for just a minute. I have 2 terms. They're being subtracted. Is everything in the problem a perfect square? Well, 9 is a perfect square. It's actually 3 times 3. x squared is a perfect square. It's actually x times x. And 1 can be a perfect square. It's actually 1 times 1. So you got to break it down into the root of every term. So the root of 9x squared, if I break it down, is 3x. If I do 3x times 3x, that would give me 9x squared. So this is the root of 9x squared. What's the root of 1? The square root of 1, well, it's just 1. So now, my factored pair is going to be the sum of these two things and the difference of those two things. So 3x plus 1, 3x minus 1, and I'm done. It's factored. Pretty cool, huh? Let's take a look at another one. This time, let's do number 73. All right. Do I have two terms? Yes. Are they being subtracted? Yes. Are they perfect squares? Yes. 25, the root of 25 is 5 because I can do 5 times 5. That equals 25. P squared can be broken down into P times P. 16 can be broken down into 4 times 4. So what's the root of this? Well, 5P is the root of 25P squared. What's the root of 16? 4. So my factor pair is going to be the sum and the difference of those two roots. I'm done. All set. Let's take a look at number 72. Number 72, I have 1, which can be 1 times 1, and I have k squared, which can be k times k. So the root here is 1, the root here is k, and I'm going to have the sum and the difference of both of those. Pretty sweet. Why don't you take a look at number 74, give this one a try on your own, pause the video, and come on back when you think you've got it. How'd you do? Did you get 2r plus 1, 2r minus 1? I hope you did. Let's keep working together. Take a look at number 75. Now, I would not be a very nice person if I told you to go try 75 all on your own. Why? Why would that not be very nice? Well, let's take a look. 78, let's see. Do I have two terms? Yes. Are they being subtracted? Yes. Are they perfect square? 48, that's not a perfect square. 75, it's not a perfect square either. What do we do? No sweat. Just factor out your GCF. Let's see. If I factor out from 48 and 75 a 3, then my leftover is 16b squared minus 25. Whew, that's much better because 16 can be written as 4 times 4. V is V times V, and 25 is 5 times 5. So the root here is 4V. The root here is 5. And I just need the sum and the difference of those two roots. And don't forget to bring down your greatest common factor. You factored it out in the beginning. Don't forget to put it back in at the end. We're going to bring him down and put him into our final answer. So we've got our factor pair and our GCF, and we are good to go. All right, let's take another look at one together. Let's take a look at 76. There's actually two ways that you can do this, okay? You could factor out the GCF at the beginning, or you can factor out the GCF at the end. Well, wait a minute. How come all of a sudden there's two different ways? Well, because 100 is a perfect square. 16 is a perfect square. But they're also both even numbers, which means we could definitely factor some stuff out. Let's take a look at what we're talking about here. Let's talk about taking the GCF out at the beginning. This is the best way. This is my preferred way. I want you to do it this way. Always take out a GCF first before you do anything else. But just in case you miss it, I want you to see that it's possible to catch that GCF at the end, and that's okay. So GCF at the beginning. Well, looking at 100 and 16, I know that both of these can be divided by 4. So I'm going to factor out a 4. And if I do that, then I'm left with 25x squared minus 4. 25 and 4 are both perfect squares. So my difference of squares rule still applies. I have two terms, they're being subtracted, they're both perfect squares. So this can be 5 times 5 and x times x. This is 2 times 2. So I have 5x plus 2 and 5x minus 2. Don't forget to bring down my GCF. And there's my final answer. And that totally works. But what if you didn't catch it? What if you said, 100 is a perfect square, 16 is a perfect square, bam, difference of squares, I'm ready to rock and roll. Then you would do this. Let's see, if you have 100x squared minus 16. So you say, well, 100 is just 10 times 10. X is x times x. 16 is 4 times 4. So that means that I have 10x, because that's my root here, 10x, and here my root is 4. So 10x plus 4 and 10x minus 4. And then you look at it and you say, wait a minute, these are both even numbers. And these are both even numbers. That means at the very least I could still factor out a 2. Remember, you want to keep factoring, keep pulling things out until you are all done and there's nothing else that you can pull out. So let's do that now. We're going to factor out a 2, which leaves us 5x plus 2 here. Factor out a 2 leaves us 5x minus 2 there. And I'm going to take these two coefficients and I'm going to multiply them together. So I have 4 times 5x plus 2 and 5x minus 2. And our answer has worked out to be the same and we're all set. Okay, I'm going to set up 77. This is 77, not this one. Just kidding. 77 and 78. I'm going to set them up for you. And then I want you to try them on your own. So let's take a look. 18 and 32. Well, 18 is not a perfect square, and neither is 32. But if we factor out a 2, then we're left with 9x squared minus 16. Now, 9 and 16 are both perfect squares, and they're being subtracted. So now our difference of squares rule will work. And I want you to try that one on your own. 78, same thing. 48 is not a perfect square, and neither is 27. But if I factor out a 3, then I'm left with 16n squared minus 9. And 16 is a perfect square, and 9 is a perfect square. So our difference of squares rule will work. So pause the video, give these a try, and then come on back when you think you've got it. So these are the answers that you should have gotten from doing the perfect squares or the difference of squares rule on these two problems. Did you get them? I hope you did.